The Rutledge group works on developing an understanding of the way materials, in particular polymers, plastics, behave as a result of their molecular structure. And we do that through a couple of experimental and computational methodologies. So one focus area of my group is what I call process, structure, property relationships. And we pursue this through an avenue of using molecular modeling to develop detailed models of the molecular structure of plastics. And then we use these to predict what their properties will be. And in addition, we need to understand how this structure evolves as a function of the processing steps that the manufacturer will put the plastic through, because this also has a big effect on the properties. So to give you an idea of what we're talking about when we discuss plastics and polymers, this is a huge field. It's been around for 60 years. Natural polymers go back centuries. But the modern area of plastics, high performance and engineering plastics, begins with the invention of things like nylon and polyester in the early part of the last century. Today, in the US alone, there's something on the order of 33 million tons of plastics sold, of which remarkably about 2/3 of it is a very simple chemical composition, but the way in which the scientists and engineers have learned to assemble the molecules from this polyolefin composition gives them very different types of properties. And so I'm talking about everything from the plastic, the polyethylene and polypropylene that go into your grocery bags and drinking bottles, to what we call engineered plastics like fibers and films. An example would be a nylon or polyester fiber that's used in climbing ropes or sailboat sails or cables for bridges, including also the kind of materials that are very high performance materials. So for example, the polymers that go into body armor, soft body armor, Kevlar and Spectra, these are also high performance plastics. And in fact, the chemistry, the chemical composition of the fiber that goes into Spectra, which is soft body armor, is the same composition that goes into grocery bags. Okay? But what the engineers and scientists do in forming these molecules and then processing them into either a very inexpensive plastic bag or a very high-performing fiber makes all the difference in their final properties. So it's this connection that we're trying to understand in my laboratory from a very fundamental modeling viewpoint. We can look at the kind of properties that are important today in making more high-performing materials. Typically, polymers are used to replace other materials in applications where lightweight but high-performing mechanical properties are needed. So for example, you hear about the composites that are used in the 787. This is a carbon fiber reinforced plastic material. But also polymers are moving more, they're developing plastics with electrical properties, soft electronics. So again, you're looking at a foldable electronic material. This is something which has electrical properties, but on top of that, it's also foldable, flexible, and lightweight. So lightweight, tough, strong are hallmarks of the performance, the engineered plastics that are continuing to be developed and used in a variety of technologies today. Now, the way we approach this problem, I think, is not necessarily driven so much by what industry is asking for today, but by the fact that for the past 60, 80 years, plastics have been developed more or less through an empiricism. That something is made, its properties are useful, and it begins to make inroads into various other dependent technologies. Our interest in developing models of these materials is very much more fundamental in nature. We try to understand why the materials that we have exhibit the properties they do. What is it about a polyethylene that's processed one way versus a polyethylene that's processed in a different way that leads to this very broad range, distinct behaviors of the two materials. So this is very much sort of a blue sky intellectual exercise, very good for the university environment, educating students, and allows us to learn a lot about why materials behave the way they do. Of course, if you then go into applications, you can ask very different sorts of questions, such as, If I have an idea and want to commercialize it, I want to know if I do something in particular to a plastic material, how will it change the properties? Well, you can't answer that unless you have some sort of predictive model with which to anticipate what those changes will be. Otherwise, you have to go into the lab, make the material, optimize it, test it, and this can be a very time-consuming and laborious process, and often leads to many dead ends that are counterproductive and costly. So it'd be very helpful to have the sort of fundamental knowledge of why materials behave the way they do, and then use those models in a more predictive fashion to say how a certain change would lead to a new, what would be the effect of a certain change in the material to its properties. There's a third version of this which is also important, which is sort of the holy grail, which is if I'm in a company and my customer comes to me and says, I want such and such a property. I want something which is lightweight and twice as tough as what's currently out there. What change do I need to make to the plastic to get there? So that's the design problem. And again, you need the predictive models to be able to go through the various design options to try to figure out, anticipate what changes, anticipate ahead of time which changes would lead to the sort of customer desired properties that are ultimately desired.